Alright, this is going to be the last video before I head to bed, because I've once again been up for 24 hours. I just keep doing this. But I'm all good. I'm good. Alright. This basically is just derivatives and limits, right? Basic derivative rules and the limit definition. So, find the derivative of f at x equals blah at x equals 2 by definition. So I provided the definition here. Right, we just have the limit as h approaches 0, which is some constant, some shift, of fx plus h minus f at x over h. Right. If you want to know why this works or where this comes from, I guess I could make another video on that. I did come up with my own way of deriving this a few years ago, but yeah, it's gonna take a bit longer than what should be in this video, as you guys just want the content. So I can do that in another video. But yeah, so we want to find the derivative by definition. So this is the limit definition at a point 2. So what we can do is for x, we can just do, well, f prime, which is going to be the derivative, at point 2 is equal to, sub our values into here. So we have 2, limit h goes to 0 for our function. Right, we're subbing this into our function here. Right, we're not subbing in 2 directly and then just saying 2 plus h. No. Into here. So x plus h goes into here, and f at x goes into here. So what that gives us is 2 plus h squared minus 3, right? This piece. Minus, then just 2 squared minus 3. So over h. Make sure that you always write the limit here. The only time that you're going to get rid of this is once you sub it in, right? So once you've arrived at a point where you can sub it in without getting like a 0 case, like 0 over 0, or just something over 0, then you can put it in, right? Those wouldn't work. The ultimate goal is just basically being able to factor this out, or get a denominator such that having a 0 there wouldn't necessarily result in it going to 0 itself. Right. But yeah, so just do this, expand this, collect like terms, simplify. We find that all the constants cancel. We're left with h. Well, as I said earlier, we want to find a way to get rid of the h on the bottom so we can sub it in, because we do not want something over 0. So just factor out an h, cancel them out. We get h plus 4. Limit as h goes to 0. Since h is going to 0 for h plus 4, we can just sub in 0 here. And we get 0 plus 4, it goes to 4. I know some people don't like to use the word sub in 0, because you can use epsilon delta proofs, but yeah, that's not what this course is about. I've actually seen some people get mad at that, which is ridiculous, but yeah, if you want to see epsilon delta proofs, you can do that yourself later, or I could show you, but yes. Okay, 2. Find the derivative of f at x equals x times the absolute value of x at x equals 0 by definition. So once again, I just put the definition here, and I showed you guys a little example of what an absolute value function would be, because this is going to be important later on. If you want a way to visualize this, well, I guess we can start by graphing it, right? So imagine we had like x minus a. How do we know where it's going to be here? Well, we can set this equal to 0. And here's the thing that I saw some people do that is not okay to do. They say like, well, the absolute value, well, that's just going to imply everything inside is going to go to positive, right? So we're going to have positive x, positive a equals 0. Well, that's just going to give us x is equal to negative a. The problem here is, watch what happens when we sub it back in. That is definitely not equal to 0. So the rule here is if you're not solving something, sure, you can do this, right? You can say everything here goes positive, just collect all like terms. If you're solving for something though, you have to make sure to keep the signs, right? So this would actually go to x minus a equals 0, x equals a. And then when we sub this back in, what are we going to get? 0 equals 0. Yes. So there you go. That's why we would do this. We would not set everything positive. Yeah, so we know that's at a. Let's just say a is greater than 0, right? So it's going to be somewhere over here. So to the right of this point, it's going to end up looking positive like this. And to the left, it's going to be like this, right? It's going to have a negative slope. So we can say like negative m Here's just going to be positive m, and this is just important for like understanding how we're going to approach the problem later, right? So look at what I did up here. So you can like test this yourself to see that this is the case, and this is how you go about solving it, and then graphing it. If we had some shift, it would just be moving up or down. Plus c, plus d. Maybe we have like some coefficient here, reflecting it, like, I don't know, k. Yeah, but here we go. Absolute value x minus a is equal to this. It's equal to the set of the positive case and the negative case, right? Because look, we have positive slope here, negative slope here. So we need to split it up. So we generally do the positive case is just x, well, itself, such that x is greater than or equal to whatever value the root of here, right? Whatever the root is. Because it's going to be at that point that it's going to go positive, negative slope. So the negative case is just going to be less than that, right? Because we want these to match up. Greater than, equal, less than. Okay. But yeah, so using that, we're going to start this here. So we want it at 0, so we're going to say f prime of 0 is equal to the limit h goes to 0 because we're using the definition. Just sub our points in once again, right? We have 0 plus h. So here this x would go 0 plus h, this would go 0 plus h, minus, and then f at x, that's just x and x, would go 0, 0 over h. So what we get here is just 0 plus h, that's just h, and absolute value of 0 plus h is just h. So we get h, absolute value h. We can cancel out the h's on the bottom. Then we arrive at lim h goes to 0 for the absolute value of h. Now what we're going to do is we're going to use our piece over here. This is why I talked about it, right? Because we can split this up into two different cases, right? The positive and the negative. We do not have any shift, so it's going to be greater than or equal to 0, less than 0. Or you can solve for that. That's just simply, right? So in the case that we're splitting it up into positive and negative cases, well, we see that this is greater than or equal to 0, so this is going to be our positive case. And this is less than 0, so this is going to be our negative case, right? And so when we write the limits, we have, h goes to 0 positive, lim h goes to 0 negative. If those two are equal, then we can just say lim h 0 goes to whatever those two go to, right? If this is like, say this is equal to k and this is equal to k, then we can say the limit itself is equal to k. Yeah, so we split that up. We get the positive case here, the negative case here. It's approaching 0, so we can just sub our 0 in here. We get 0 and 0. So we can just say, therefore, the limit as x goes to 0 for f at x, right? Because it's by the definition. That's just going to be equal to 0, because the left side is equal to the right side, as I said over here, right? Or we just be like, this is equal to this, equal to this, equal to this. There you go. If they were not equal on both sides, then you would say it diverges, right? They are not the same, the limit does not exist. You can use a bunch of terminology, just depends on the context, right? You can say like, oh, shoots up to infinity here and a negative infinity there. Infinite divergence, jump discontinuity. Yeah, you can just have a lot. Does not exist. Okay. Number 3, since we have a function here, we can say f at x, this is g of x. We can use the product rule, right? That's just the derivative of the first one times the second one plus the first one times the derivative of the second one. So if we're going to go about doing this, right, we're going to set up the derivative like this. First, second. First, second. Then we're going to use the power rule. In case you're not familiar with that, I know we worked on it a bit, but not that much. Say we had like the derivative of, let's say a to the xn. Well, this is just going to be equal to n. We're going to bring the n down. Our coefficient a, x to the n minus 1, right? So you see what we did there? We brought the n down. We subtracted the power by 1, and that's it. So if we were to do it again, I'm just giving this in case people aren't, they don't know what it is, right? If you know what it is, that's good. We're going to bring it down again. And we're going to do n minus 1 again, right? And we just keep this pattern going on and on and on and on. Right, so that's the power rule. But yeah, so we're going to use that. Right, derivative of the first power rule. This is power rule. Then what we're going to want to do is we're going to want to expand in, because we're going to want to collect like terms. If it does not ask you to simplify on a test or exam, whatever, you can just stop here. That is enough, right? If it wants you to simplify and expand, well, you're going to need to get all the way down to here. So yeah, we do that. We see that after we simplify these terms over here, we get this. Square root x over 2 over 3x, right? That just goes to x to the 1 over 6. We notice that these are similar, so we can collect them, bring them here. Yeah, that's it for that. So this is another new one, I think. Yeah. I did all the tutorials out of order, so yeah, I'm not quite sure, but yeah, so it's find the derivative y at position 1 versus respect to this function. Okay, so here we can use the quotient rule. You can also use the power rule, right? You can rewrite it like this. And then you'd have to use the chain rule though, right? Because we have a function inside of another function, right? You can imagine this is f at x inside of -1, where we have g of x. But yeah, I would not do it this way. This way is just a lot messier to deal with, and there's, depending on what you have, it can actually get really, really bad. The quotient rule is always a good idea. So yeah, the quotient rule, I wrote it down over here. It's just the derivative of the top times the bottom minus the top times the derivative of the bottom over the bottom squared. So I wrote that over here. This is the top, this is the bottom, derivative. Once again, if you're writing a test and exam, if it does not tell you to simplify, you can stop here. Right? At least for me. I would clarify that with the professor. That could be a individualistic thing. But yeah. So anyways, once we get to this step, we can actually, instead of just like simplifying and expanding, we can just sub our value in directly right away, right? We have the derivative here. We don't need to work on like doing like, 5 different steps to simplify this. Let's just sub our value in and get it right away. So let's put, therefore, y prime 1 is equal to, where all of our x's are, we put the 1. We see after we do that, this is just going to go to, well, 2 minus 1, 1 times square root of 1 is just 1 minus 1 this, 1 squared, minus 1, that's 0, plus 3, times this is 3 over 2, so we get 1 minus 3 over 2. Then here, we're going to use a little rule where if we have 1 over a plus 1 over b, this is equal to b times 1 plus a times 1 over a times b, because we're equating the denominators in order to like actually collect them like terms, which is equal to b plus a over ab, right? So we use that here to get, well, multiply this over here. We have an invisible 1 here. So we get 2 minus 3 over 2, which just goes to -1 over 2.